everybody, and welcome to a new video. I'm going to explain conics, the types, the elements, and the eccentricity of conics in this video. And um, so first of all, we'll talk about the types of conics, the parabola, the ellipse, and the hyperbola. Then we'll move on to the elements, the vertex, focus, directrix, and eccentricity, and then to the characteristics of the eccentricity of each type of conic. So first of all, why exactly are they called conics? The word conic is derived from the word cone. As you can see here, we've got two cones, one above the other, and we'll try to cut these cones so as to get the three different types of conics that we had already mentioned here. So if I were to cut my cone like this, the surface of the cut would look like this, which would render it as a parabola. Now, what if I decided to cut my cone using a tilted straight line? So what if I had cut my cone like this? I would have gotten this shape on the surface of the cut, which is an ellipse. Now, as for the hyperbola, I'd have to use both cones to get a hyperbola. So I would cut this cone like this, just like we did with the parabola, and then I'd move on to the cone above it to its counterpart and cut it the same way. So in this case, we would get two different parabolas making a hyperbola. So a hyperbola is pretty much two parabolas, okay, two identical parabolas, meaning a pair of parabolas. So that's for how to draw a conic starting from a cone, how to cut a cone into a conic. Now, moving on to the elements of the conics, we've got the vertex, which is basically the edge of a conic. In the case of the parabola, we had seen that the parabola being drawn this way has only one vertex, which would be somewhere over here. As for the ellipse, it's going to have four vertices, and the hyperbola is going to have two vertices, as it represents two parabolas, each parabola having one vertex would give us two vertices. We'll start by drawing a parabola, so we can talk about the focus directrix and the relation between the focus and the directrix with respect to the eccentricity, because the eccentricity depends on the focus and the directrix. I'll start by drawing you guys a parabola. This is a parabola. This is the focus of the parabola, point F. Point M is any point on the parabola, and x equal minus 2 is the directrix of the parabola. I'll insert this graph and enlarge it so we can discuss it. So as you can see here, we've got a point M, which is a point on the parabola, and we've got a point F. Point F is the focus. It's given as the focus. So, and we've got this line over here, the purple line, represents the directrix. Now, why did I say before that the eccentricity depends on the focus and the directrix so as to be determined? The eccentricity basically means length of MF over the distance from M to the directrix. M in this case. If I were to take any other point, it would be the same case. What if I took the vertex of the parabola, which is point O of coordinates 0, 0? It would still be the length of OF over the distance from O to the directrix, which would mean this over this. So most of you must have realized that the length of MF is equal to the distance from M to the directrix, which is why the eccentricity being MF over distance from M to the directrix for a parabola is equal to 1. Then we'll draw an ellipse and a hyperbola so you can see the difference. Why is it less than 1 in an ellipse and more than 1 in a hyperbola? Now in the case of a parabola, you can see that the center of the parabola, the vertex of the parabola, in this case, point O of center of coordinates 0, 0 is the midpoint between F and the directrix and its orthogonal projection on the directrix, and it's going to be the case for any other type of parabola. The vertex of the parabola will always be the center of the vertex of the parabola, being the center of the parabola, will represent the midpoint between the focus and its orthogonal projection in the case of the parabola. Moving on, we're going to draw an ellipse so to discuss it. In the case of an ellipse, you'll see that we'll have more than one vertex, more than one focus, and more than one directrix. So this is an ellipse with a focus and a directrix. There it goes. The focus is still point F. In this case, it's of different coordinates, but we named it F since it's the focus. Point O in this case is the center of the ellipse. Now in this case you'd see that point O isn't a vertex like in the parabola, but it's the center of the ellipse. We'll discuss what determines the center of the ellipse in the next couple of minutes. Now again, let's take any point on the ellipse. I'll decide to take point A. Point A is one of the four vertices of the ellipse. We've got point A, which is a vertex. This point over here of coordinates 0, 4 is also a vertex. This point over here of coordinates minus 5, 0 is also a vertex, and then we've got 0, minus 4 also being a vertex, which means that the ellipse has 4 vertices. Point A is a point on the ellipse. I'll suppose that it's a point just like any other point, regardless of the fact that it's a specific point, that it's a vertex of the ellipse, and I'll prove that the eccentricity of an ellipse is less than 1. So again, we took this point, the eccentricity would be the length of AF, which means the length of the point, the segment, which includes the point and the focus, over the distance from the point to the directrix, which means that the eccentricity in this case is AF over distance from A to the directrix. Obviously, AF is smaller than or less than the distance from A to the directrix, which renders the eccentricity of an ellipse less than 1. Then again, O being the center of the ellipse would also make it the midpoint between the vertex A and its counterpart over here. Being the center, it would also render it the midpoint between F and its counterpart over here. So we've got to know that in the case of the parabola, the center is also the vertex, and it represents the midpoint between F, between the vertex and the directrix, between the focus and the directrix. In the case of the ellipse, we realize that the center of the ellipse, in this case being O, is the midpoint between A and its counterpart, which is the other vertex on the same axis, and between F and its counterpart, which is the second focus on the other side. Now, having a second focus means that we've got also another directrix. O again is the midpoint between this directrix and the directrix on the negative side of the abscissa. Moving on, I'll draw you guys a hyperbola so we can discuss it. So I'm deleting the ellipse so we can draw a hyperbola. This is the hyperbola. That's the focus, A is the vertex, and we've got the directrix. I'll enlarge it and we'll discuss it. Again, I'm going to choose a point on the hyperbola and let it be A, which is also a vertex. AF over distance from A to the directrix is greater than 1, since AF, according to this graph, is greater than the distance from A to the directrix, which makes the eccentricity of a hyperbola always greater than 1. We could choose any point. If I were to choose this point over here, you'd see that the length from this point over here that I'm going to choose towards F is much greater than the distance towards the directrix from the same point, which is why the eccentricity of a hyperbola is always greater than 1. And do note that when talking about a specific parabola, a specific ellipse, or a specific hyperbola, no matter what point we choose, any point on the hyperbola, ellipse, or parabola, as long as it is the same conic, the eccentricity will always be the same. Now, if we were to change the elements of the conic, the focus, directrix, or vertex, then obviously the eccentricity would differ, but always within the boundaries set by the properties of each conic. So for a parabola, the eccentricity will always be equal to 1, regardless of the position of the vertex or the position of the focus. For the ellipse, it's always going to be less than 1, but it might be 0.6 for one ellipse and 0.8 for another. For the hyperbola, same case. It might be 1.2 for one hyperbola, and it might be 1.5 or 2 or 3 for another hyperbola. So that was basically an introduction to conics, to the types of conics, their elements, and the characteristics of the eccentricity of each type of conic. In another video, we'll discuss the parabola, the ellipse, and the hyperbola in details. We'll talk about the tangency when it comes to conics. We will talk about finding the focus, finding the directrix ourselves without having it being given, and we'll solve a couple of exercises on this lesson. Thank you for watching this video, and any comments are appreciated. Have a nice day.